Joseph, when do you want me to start?
You can start now.
All right. Well, ladies and gentlemen, it's my pleasure to introduce Ted Godo. During his geologic career, Ted spent 35 years at Shell Oil, rising to the level of chief geologist for Western Hemisphere, then retiring and working at Murphy Oil for 5 years. And he is now a geologic consultant at Geodot Exploration. Ted has published on Mississippi age turbidites, Chert and evacuolite formations, Gulf of Mexico, Cenozoic turbidites, and most recently on the Jurassic Norphlet Aeolian sandstones. Ted's efforts and his persistence led Shell to discover a giant deepwater field, Appomattox, in 2010. His two papers on this discovery, Related Wells and its Norphlet Reservoir, published in 2017 and 2019, are the most definitive in understanding this very complex play, which is now one of the largest in terms of ultimate technically recoverable resources, second only to the Wilcox subsalt play. And as you'll see, Ted also has a clear passion for Civil War history and battles. Ted?
Yeah, thank you very much. I appreciate it, Dr. Snedden. Today's talk will summarize the main points of a recent paper highlighted at the top here, which details results of 10 wells in the play having different outcomes. On the right is a picture of an active wind blowing off a sand ridge crest and where the winds carry off the fines, leaving coarser grains to sort and fall down in the avalanche slope. Below is a core of the Norphlet showing these avalanche beds and team members studying the core. On the left are pictures of the algal or organic laminations in the Smackover-Carbonate source rock member. The top picture is a sidewall core fluorescing in ultraviolet light, and immediately below that is a picture of a ditch cutting from Shiloh showing the laminations. The middle picture is just taken from the USGS professional paper on global sand seas, and I colored it and modified it a little bit to show the Norphlet depositional model of sand ergs separated by exposed salt walls, which is what I believe is the model here in the deepwater play. There are 47 slides in this presentation, so you can keep track of the slide number in the lower right if you get bored or if you have questions. This map shows the distribution of the onshore and offshore well control that penetrates the Norphlet section from East Texas throughout the Gulf Coast states and into the present-day deepwater Gulf of Mexico. The Norphlet was first penetrated in 1940 and up in this position here. Let me put the laser pointer right up here, near the town of Norphlet. And the towns of Smackover and Louann are also within miles of each other there, and whose names are now used for formations that are obviously well known. It wasn't until 1967, drilling for CO2 in this area around Jackson Dome in Cretaceous reservoirs, that some went deeper and found two wells found thick Norphlet Aeolian dune sands, one bearing CO2 in one field, and the other one was oil for the first time. So 1967 was the first time they actually found, good sand in it. The furthest up dip, so regionally now, the furthest up dip limit of the Norphlet is also coincident with the up dip limit of the Louann Salt, shown here in pink. The environment of deposition for the the environment of deposition for the Norphlet is fluvial and alluvial fans in the up dip position in the brown, with Aeolian sand ergs shown mainly in yellow. The uncolored areas out in here where there's well control, these are all the well controls that went down to the Norphlet. The uncolored areas are basically Norphlet, are wells that found Smackover directly on salt, so no Norphlet out in these areas. Shown here are the downward sag maximums or basins separated by the ridges or highs in the brown outlines. So, you have the East Texas, North Louisiana Basin, Mississippi Salt Basin, the Conecuh Embayment, Destin Dome, and then finally out here in the red box is the deepwater play with all of the wells in black dots. And again, the purpose of writing this paper is to present a hypothesis that the integration of three critical factors are required to produce large fields or otherwise economic tieback fields. And if you don't have all three, you get a dry hole. This is a map of each of the wells positions in the deepwater play that targeted the Norphlet. Shown in the colored polygons are the named well locations. The polygons are actually mapped individual chips or basins that are surrounded in the uncolored area by salt ridges, ridges and domes. So the Norphlet is actually, each one of those represents an individual fetch area for it. So they can be quite small, and some are larger, but that's what they are. The Norphlet sits immediately on the salt, as you'll see from the strat section, or you already know that. And with subsidence, the salt's evacuated beneath these basins or polygon areas and rise laterally, which separates them with the salt ridges. The exposed highland area during Norphlet deposition is in the east. You can see the little mountain-like things and some rivers. That's not perennial rivers, but just where water would flow when it did rain. That's called the Middle Ground Arch or Southern Platform by some. The pink line, again, represents both the up-dip limit of the salt and the Norphlet. Dark brown areas represent the areas most likely for alluvial fan deposits, as seen in a lot of onshore penetrations where there's well control, while the tan areas are fluvial outwash deposits. We'll talk more about that, of the Norphlet onto an exposed, flat Louann Salt flat. The orange area are local thicks, referred to as pothole basins, which generally line up southeast to northwest. I won't talk about their origin today. They're very interesting, other than to say they are collection points for mostly thick fluvial wash deposits. The area in yellow are dominated by Aeolian sand ergs, and they're composed primarily of dune and sheet sand deposits. This slide summarizes the 10 Norphlet wells in the paper. The top row of the three columns are burial histories. We'll talk more about that here as we go. This is basically with time, so this is old versus young. So maturation went up into a peak here, and then it went flat. Mainly this flat is during the Paleogene time, where there was very little sedimentations in the Eastern Gulf. And then the Miocene time comes, and then there's another pulse. Some waited for a while before, not much burial, until the Miocene burial, and then all of a sudden they go up. That's what you want. And then sometimes there are prospects over in this column that have what you want in terms of burial, but the reservoirs, you can see, well, the color of the reservoir here is mainly low permeability fluvial. That's not good. We'll explain why later. Even though it's got a good burial history, that's one factor. The other factor is permeable sands, and they don't have it. So these are dry holes. So what you want is things here in the middle. If you charge too early, you'll get residual columns, and that's residual here in this hatched one. Under simple closures, you can still get some live oil, but below that, you just see that they're residual, and we'll talk more about those as we go. This slide will serve as an introduction for the stratigraphic position of the Norphlet. The chart was also drawn to show the lateral changes in the overlying rocks as well, which had a big difference in burial. The Norphlet over here would have had been buried early by a lot of big shelf sediments, but there's a marked shelf sediment decrease as you go off the Cretaceous shelf edge, and so wells for the Norphlet out in here have a much later depth of burial, mainly by the Cenozoic. So to summarize, the three criteria are burial history is critical to determine the peak of oil, timing of peak oil expulsion. Only recently charged structures, that is within 15 million years, mid-Miocene, have a chance to really fully fill the trap. Earlier charged prospects, say the Cretaceous 65 million years ago, demonstrate a slow, nearly complete leakage during this time. It seeps out. Second one is a minimum Smackover source rock maturity. It should really have a VRE of 0.9 or more, and of course a larger fetch area if you can get it. But mainly maturity needs to really crank up because of the kinetics and source rock quality. It's not as good as the Tithonian, so you've got to really jack that maturity level up. And then the third summary is that you need good and effective permeability. I'm talking permeability, not necessarily porosity, because the permeability allows subsurface fluids to move through the Norphlet, creating a lower pressured sink for this downward charge. Above it is pretty tight rock, and we'll talk a little bit more about the mechanics of how this works. But the lower pressure Norphlet enables the overlying maturing and higher pressured source rocks to expel the downward into the Norphlet. Here are cross sections to illustrate the burial difference for the Smackover-Norphlet, shown as the yellow event down here at the bottom, just above the salt. The Jurassic, Cretaceous, and Cenozoic burial differences at pseudo well locations A, B, C, and D are placed to show various variations in the charge timing. That would be down here. So something at D, for example, charged, it's 100 million years right here, charged really early, and then that means the retention time in the trap has to last for 100 million years. Other ones, you know, this is still a long time, but yet other ones like this one, for example, A, that's the one that here is, it really didn't have much sediment on it. If you're down here, that's the cold Cretaceous. That's not enough to mature it. And only when you dumped in this whole Cenozoic, mainly Miocene, is when you turned it on. That's what you want. That's the best way. To charge the Norphlet, the overlying Smackover source rocks need to expel downward, as we said, and do so by a combination of becoming a bit overpressured in the source rock due to maturation. But to get the charge to move downward requires that the Norphlet to be a permeable horizon such that a relative pressure sink can accept and move hydrocarbons laterally to relieve this pressure buildup in the source rock. The figure is a plot of the formation pressure estimate plotted with the actual mud weight used. This is an Appomattox well, that's typical of all the discoveries. And the mud weights are in the orange dots here. You can see the blow up on the right and the deviation from this normal increasing pressure is a slight amount, maybe about a pound or pound and a half overpressured relative to the permeable reservoir underneath it. And when you get that, the pressure, the oil moves downward. Here's a Smackover log. It's a gamma ray and resistivity log of a typical Smackover section. This one's from Appomattox. Smackover members are color coded in the center column here. Just lower middle, basal conglomerate, piedol, high density, and red shale. And the center column, or this one over here, shows the two types of carbonate source rocks that we have. The two types can be modeled as a clay poor, or in other words, high carbonate, rich in algal laminations, and a clay rich, which just means marl. And so this talk will only briefly describe the source rock's position here, located about 400 to 500 feet above the Norphlet section. We can have other talks that talk specifically about the kinetics and quality, but in here, we're just going to talk about mainly the position and maturation needed. Summarily speaking, I guess, with heating and maturation occurring, high pore pressures are induced in the source rock, with the first oil filling micropores and any other pore space. And then with continued maturation, pressures can only be alleviated by microfracturing. If this Norphlet has permeability, then oil will move downward from above into the Norphlet and then laterally up to a higher, less buried crest to relieve that pressure. Maturing source rock on the structural crest itself can still have pressure relief by charging downward and vertically filling the Norphlet. This little inset here is showing microfracturing with the resulting pathways for oil to move through. They've been described as stringer paths by Hanschel and Karoff's really good book that shows here about how far you can take the source rock and charge down and then move it up into the reservoir. Staying with the Smackover, this graph shows how the oil, the graph shows how the amount of oil expels depends on the degree of thermal maturity, as illustrated in these two wells, Gettysburg and Rydberg. They both have a similar fetch area. One has a higher maturity than the other. And so it was able to squeeze out more because of the higher VR, more oil. And so in Rydberg, you got a 100 million barrel field, and in Gettysburg, you got about a 35. It could maybe be a tieback, but right now, MMS didn't like how long it was going to take to have it hooked up, so it's back available again. So essentially, it's a sub-commercial discovery. So now the third one is permeability. So in this log, it's from Petersburg, the Norphlet's composed of nearly all fluvial or water lane deposits, not much Aeolian. And as a result, the well shows calculated permeability determined by an NMR log here in yellow, and spot check with rotary sidewall cores in red in the far right, in this far right column. The dip meter, hard to read in here, shows dip ranges hovering around 10 degrees, which when compared to Aeolian dune dip sequences, Aeolian dunes exhibit dips up to 30 degrees on slip faces. And the slip faces or avalanche bends are characteristically seen in whole core and in dip meter logs. Here is a well log from the Gettysburg oil discovery in Aeolian dunes that shows that they were cored in this position right here across the oil water contact, which is right here. They also have, the dip meter's not on here, but they show dips up to 25 to 30 degrees. But note the permeability difference in the far right here. It's hard to read, but you have basically, I'll put a cheat sheet up here, tens to hundreds of millidarcies, whereas in here, all less than 1 millidarcy of permeability. So it's a huge difference. In this example at Fredericksburg, the map here shows the well drilled inside the four-way dipping simple closure with the overlying Smackover is mature, with several of the sidewall cores in the Smackover that was recovered actually bleeding oil. However, the Norphlet sand section was entirely red colored. I'll talk about that in a minute. It's not bleached. And there was no other direct hydrocarbon shows of any type. The permeability seen from the previous slide was very low, and it's not enough to generate a potentiometric low relative to the overpressured that happened to be a maturing source rock. This slide is a very similar well at Petersburg, which also drilled into a structural simple closure with mature source rocks overlying the Norphlet, but due to low permeability, again, the sands remained red or unbleached, and there were no traces of any hydrocarbon shows. When the Norphlet has Aeolian dune sands that have high permeabilities, and if they're present in a structural crest, like over here at Shiloh, then you get downward charge and it works well, and the structure fills with oil. However, in the case of the Shiloh well, there is evidence that the entire Norphlet may have once been filled to base. Here this is the whole core with fluorescence. There's fluorescence down here. Here's the oil water contact. There were shows, mudlog shows and cutting shows all the way down. And here's whole core with direct fluorescence. And this is way too sharp of an oil water contact to be in this low, in the permeability porosity range of this well. So it basically is a residual column that was once filled and went up to the present day oil water contact. We're going to show a little bit more about that in the next 2 slides. Here's another example from Titan when so in Titan, it found good permeable sands as well beneath the mature source rock. It had 11 feet of oil right up at the top, but the rest of this, we've got sidewall cores. It's in the paper there as well, but it looks like somewhere down the red color changes about this position. And so this is about where we think the paleo charge was. And then with time, it imbibed or drained upwards, leaving only 11 feet of active column. And to illustrate those, we look here, it's just a summary of 3 seismic lines. Shiloh here in the middle, and Titan, and then there's another one, Antietam, similar results. The seismic shows that the present day oil water contact level matches the point where the overpressured basal Smackover seal loses its simple closure. So right here, this is where the well drilled. It found 11 feet of oil. And if you look at this roll, and if you believe it completely, obviously there's some oil in there trapped. It looks like that there's enough simple closure here to retain that. It's an overpressured seal here, but the column that was on down through here, whether it leaked up through the fault or whether it just leaked because of juxtaposition, change in the wettability over time, it leaked and came up. There's all sorts of shows up here above, so hydrocarbon would have just tried to find its way up the section. The same thing at Shiloh. There is a little fault right here, but it's not enough to offset the basal seal, which is this blue. And the oil water contact in the well goes right to here. So again, it would have, anything older than this or deeper than this would have been juxtaposed to younger sediments. And with changing capillarities, presumably, the column rose. Here's Antietam, same sort of thing. There's just enough roll here, and it found this much live oil. These are some pictures. These are documented in the paper if you want to see that a little bit more. But if you get recent charge, as in Appomattox, it demonstrates that small sub-seismic seals may hold back significant oil columns. The log on the left is one of the first appraisal wells drilled at Appomattox. On the cross section, the first well was drilled down through here and found pay to base. That's the #1 well. Let me see. So that would be here on the structure. And then the well was sidetracked down, which I don't show right here, and it was still pay to base. So we came back up and we drilled basically a horizontal well, staying in the Norphlet, or trying to, staying in the Norphlet to find a water contact, but it didn't, it drifted upward, it bumped its head on the Smackover in this section right here before we changed and said dive, dive, and we went on down, get back in the formation and found the oil water contact here, which is this point here on the map. And it has about 1,900 feet of closure. So the well went on down and drilled the salt so we know how thick it is. This is a TBD log here that we see. Because, let me see here. So on the structure map, there was no apparent seal. So ignore what this is. There's a lot of question marks. We saw the contact down here. This fault ended here. This one really wasn't relevant. And so it looked like, you know, if this contact here went across, then somewhere up in this position, you know, you ought to have a pretty deep column. Now, what the trap is, we didn't know. So, you know, that's what was happening. We thought that we drilled this well thinking that the spill point probably was this synclinal spill point out here. And in fact, it is. When they ended up setting here, they drilled down dip just to see if it might have a big column, not knowing really what the trap would be. It was all wet. Sidetracked up dip, found what's probably the column here that's trapped here. So the question is, what's the seal across this top? Is it abundant deformation bands, which were present in the discovery well and less so as you move down dip? Or are there small faults, or is there a pinch out? Is it stratigraphic? Whatever these seals are, they're likely only temporal seals, though, as we've seen from the previous examples at Shiloh, Antietam, and Titan. Here's another discovery with recent charge. It's at Vicksburg. It also illustrates how this recent mid-Miocene time charge enables an otherwise subtle flow barriers maybe to actually seal different oil accumulations. Vicksburg was drilled by 2 wells separated by a fault. Here's the first well. It's actually B. That was the first well drilled, and then more recently they drilled the A location over here. Both wells found stacked Norphlet Dune sequences with an oil water column whose fill is different between these 2 wells. At this point, this fault really kind of died out. So we drilled this well, we saw that oil water contact, saw that there's quite a bit of sand here. There's only a couple hundred feet of fault displacement here. You'd have sand on sand. There was no reason to believe that this water contact necessarily would be any different than here, that it would just sand on sand, fill around and be in that position. But instead, there seems to be this fault. Here's a picture out of Fosson's book where deformation bands, here's some deformation bands in the outcrop. It's basically where you get grain to grain crushing along faults. They can extend out beyond the tip line of normal offset measured based on seismic and can extend quite a ways out. There's been a lot of outcrop studies, and we've seen there's a huge permeability difference across these. So thinking back to Appomattox, that might be at the crest, that may be the seal. But if so, that's a heck of a lot more column than the 175 feet of column difference between these 2 wells on either side of the fault. So again, burial history is critical. You need recent charge. You need the Smackover to kind of heat up above 0.9. And you need good effective permeability. So we talk a little bit about the red colors of the sand and the bleaching as one way to kind of help you with understanding residual oil columns. Here's Gettysburg drilled a structural closure as shown on this index map on the right here. The log on the left side, and note the position of the whole core taken across the oil water contact. There's some dip meter results. So it's nice Aeolian bed. Here's a picture of a core photo. It's only a 2-foot zone, but I chose that below the water column, something where you can see the nice avalanche beds here. And it's a representative of what the Norphlet Desert color really looked like. It's in all those fluvial ones, it's all the same red color as well. And in this Aeolian that's never been charged is also very red, hematitic, rich sand. An important change occurs though in the Norphlet when oils enters the pore system and fills the trap. First is a color change from red to brown to an olive to light gray. Munsell color chips are placed in the core photo taken in natural light, which is this column. So here's more of the olive gray, and here's the red brown, or however you'd like to describe it. On the UV side, of course, we've got nice oil filled, and this is no oil down in this section. The entire core is shown on the right. And you'll be able to see, I don't know if you can tell this color change or not. I think the next slide just kind of zeroes in on the contact. But the important thing is the XRD analysis of each 10-foot cutting in the well. And it shows, well, actually out of the core. And at the oil water contact, the hematite, which is here in red, you've got maybe 2 or 3% hematite, and as soon as it gets up above the oil water contact, it's 0. Conversely, or also the pyrite, which is 0% down in the water leg, turns and becomes pyrite in the oil column. At the oil water contact, the hematite is removed in the upper above the oil water contact, removed by the presence of organic acids associated with the oil. This creates a decarboxylation, a big word with release for me, with release of iron. The acid content of the oil appears to also cause a redox reaction, reducing the iron in the hematite to soluble ferrous iron state and precipitating it out as an iron sulfide pyrite, the yellow dots. And also it freed other iron taken into the chlorite clay, which you can see, this is the chlorite obviously gets a lot more than up in the oil column. The additional iron going into the chlorite increases the size of the chlorite, which is not good because it further reduces permeability by narrowing the pore throats. And interesting, early on in exploration, we geologists always saw that the better permeability sand in the wet zone, obviously always, thinking it might be stratigraphically controlled. And so we always made up stories how the next prospect would bring this previously wet sand up into the column and we'd get really good permeabilities. What we should have been doing is using only the porosity and permeability of oil zones from analog wells to govern the range estimate for the next prospect rather than making up stories. But you learn as you go. Here's a detailed of the same core, just kind of squashed it down, redder color here to the olive gray. So just look at it there. Here's a whole core, not entirely, but turned it on in. This is out of the Shiloh well, drilled first well in the play in 2003. And the core log on the right shows the sequencing of these predominantly dry dune facies. So you get the claniforms, and then you get the toe sets of it, the claniform, the toe sets, claniform, and so forth up. And you can say these dunes are getting quite high with these avalanche beds. So these are drier dunes than they are down here. But all of them is good permeability. There are dry and wet dunes. Drier are better. We'll talk a little bit why, but wet dunes are okay as well. We'll explain. The reason why we get permeability, good permeability, these photomicrographs and SEM photos illustrate the importance of these framework grains, mostly quartz, but all framework grains, get coated by now chlorite clay, shown as those little rosettes. This is a nice SEM picture of it. Because the Norphlet reservoir is coupled adjacent to the source rock, well, if you got to get the source rock mature, you got to expose it to higher temperatures. And if there are higher temperatures required for the source rock to mature into the oil window, then it carries along the underlying reservoir. And quartz cementation takes off very rapidly in reservoirs at 200 degrees Fahrenheit, which is barely enough temperature to mature the source rock. Reservoir temperature at Appomattox, for example, is upward of 325 degrees Fahrenheit. It's pretty hot. So without chlorite coats, quartz cementation cements the reservoir by syntaxically growing quartz along the grain C-axis into the pore space. You can see some euhedral grains here growing into the pore space where there's a little breach in the coating. And here's some cute ones here in the pore space here where there was a little bit. So, but overall, it's not enough to completely cement. So how do you get that? Well, the graph on the left comes from Tom Taylor's 2010 paper. Tom worked on the Norphlet and reservoir. He was a petrographer at Shell for a long time and done a lot of work in the Norphlet and other wells, North Sea, all sorts of places. And he has shown that grain coatings on different reservoirs make a big difference in preserving porosity from being occluded with later cement. However, because the Norphlet reservoir must endure some of the highest temperatures, clay coatings need to be at least 98%. Here's the Norphlet ones. These are from the North Sea in this example. I mean, they can work, but with the higher and higher temperatures, you got to get, even these are probably out of the tight zone, like Mobile Bay, which don't have any reservoir. The only ones that he hadn't showed on here, but I can tell you that we had a lot of discussions, and basically you need about 98% or greater coatings to preserve the porosity and permeability. To achieve this coating completeness, the pre-chlorite clay begins sticking to grains first by electrostatic forces, blowing the sand around, but then once deposited in the dune sequence, there's kind of a crude drawing I made here, but just to try to say that, a lot of days in the rain and sun cause the dusty air and clay to basically alluviate, draw down into the vadose zone. So that's why you need your sands to be, drier dunes are better just because they're going to be further away from the water table and have more days in the sun, so to speak. So they get more opportunities to get a more complete clay coating. If you don't get them coated, if you get less than 98%, even in Aeolian reservoirs, which doesn't seem to be the case, except one, which we'll show later on, they all seem to have enough days in the sun. And that has to do with subsidence, and we'll talk about that here in a little bit. But before we get there, we can just talk about an interesting observation that now can be seen in every well. And that observation is how the contact of the Norphlet Desert is overlain by the first water transgression of the Smackover. Not carbonate, just mud. The initial Smackover transgression is by a very slow flooding occurrence across a very red hematitic desert sediment. And with this slow water rise, the surface desert clays are picked up and redeposited in the clay as a really unique red colored, very clay rich shale. Where there's a salt flat, where there's a desert, flat desert, something like this, where Raptor and Madagascar are kind of hypothetically put in on this obviously recent analog, where it's just wash across through here. There's no topographically higher sand dunes in this area. And in this area where you see a 30 to 40 foot, which is this part right here, here's Madagascar, Fredericksburg, Petersburg, you see 30 to 40 foot of this red shale seen today. But on the top of every dune, you still see it, but it's only about 3 to 4 feet of this red shale. And it's a little teeny gamma ray nick if it is 4 or 5 feet, because that's about the resolution of the tool. But if you take sidewall cores, you'll find that red shale even on the top of the dune sets. And so the model is this red shale deposited very slowly, flooding the area, burying and entombing the Norphlet dunes. Here are some photomicrographs of the red shale. You can see this very characteristic red, and in thin section, it's a lot of hematite, so it's and floating grains. This next slide is also, this is out of Petersburg. Here's a rotary core, here's plain light, and cross nickels. So a little floating silt or sand grays, and otherwise just a clay matrix. Okay, so basin-wide, the Norphlet clastics surround the up-dip limits of the exposed Louann Salt, as we've kind of seen here. And we're out here around this middle ground arch, so it kind of comes around the curve here. The salt provided a mobile substrate, very important, under which rockfalls, periodic rainfall, and winds carry the sediments westerly out into the basin. Norphlet facies belts are dominated by alluvial in the most up-dip areas next to the highland, followed by clastics carried more basinward by water. And as sediments dry, they're picked up by winds and blowing them out into dunes, which are generally even the more outboard winds, and moved across this mobile substrate with mainly bark and dunes. On the right is the map on the left, I'll start with, is the current structural position. So this is how it looks right now. These are all the wells, and these are all the chips. And here's in contours are salt ridges, and then these are actually salt domes where there was thick enough salt to actually become a dome with some overhang. The salt original thickness up in here wasn't enough to create big canopies or anything. They just form bulges and ridges up and through here, and then outboard is where you start to see the domes. On the right is a possible reconstruction of chips, my version. I aligned them along paths of sediment corridors as opposed to just putting pieces together. You know, how they might connect. Here is trying to connect it with the sedimentologic process. And the sediment weight in these corridors initiated salt movement towards the edges as the salt was deflated underneath it, and then became positive salt walls and salt barriers, as we'll talk about here. Actually, there was more detailed discussion of how this early salt movement initiated. It's in the 2017 paper, talking about viscous pressure ridges and so forth. That was the 2017 paper on Appomattox. I won't talk about that here, but after deposition of the Smackover sediments, there was enough total sediment thickness coupled with more basin tilt, right? The basin starting to, that initiated the pull apart. And so that's when you started to get pull apart, and then subsequent sedimentation coming in or now would have slid some of these chips north, south, or whatever in different ways. That makes reconstruction even harder to do, but that's how you got the present day configuration. The Paradox Basin in Utah presents a really nice opportunity to observe the interaction of sediment delivered on a mobile substrate again. Outcrop exposures indicate that salt was positively exposed during deposition, sediment deposition, and formed salt walls, blocking and redirecting both fluvial and Aeolian sedimentation. The University of Leeds in the UK has a drylands consortium. It's an outstanding consortium. They study the Western US and they lead out really nice field trips. Nigel Mountney, whose work, he led some field trips for us, and his work has been hugely beneficial towards understanding you know, the Norphlet. So here are some of the depositional corridors, and here's some salt walls, and there are outcrops. You can see, you know, how some of these things were active. It's a really nice area. All right, back to the Norphlet. Here are three wells showing the common thicknesses and sediment characteristics in the play. The wells on the right over here are thin Norphlet deposited fluvially in the more up-dip position. So this is where those, thinking back to that wash coming across the desert, real flat desert, that's the entire Norphlet. It's only, you know, a couple 100 feet thick or so. Varying amounts of sand and silt in them. And then the Vicksburg well was chosen as a typical dune sequence found down dip. So you can see this is about 800 feet. There's a little fluvial at the base, so some of this wash came out early. And then not all wells have this kind of dirt at the bottom of the Aeolian sequence, but it's always at the bottom, and the dunes build out over the top. Some wells have this lower one, other ones don't. Here is some well samples from Madagascar showing the fluvial sediments that have pretty low permeability. I think I need to move on a little bit here. Here's another Madagascar with fluvial sections. You can see that there's not much permeability. And finally, this is out of Raptor, and it's a little bit of conglomeratic, just to show a little variation. But again, it's low permeability. So subsidence rate into the mobile salt substrate and relative water table rising and falling are very important. Preservation of dryland deposits, especially topographically expressed sand dune deposits, require preservation by basin subsidence. Otherwise, they just blow away and you don't get anything. So you need subsidence, but just not too much. Too much rapid subsidence, I'll try to describe here a little bit later. Professors Gary Kosurik and Karen Haverhorn, both there at University of Texas in 1993, published a landmark paper really addressing subsidence of and preservation of dry dunes and wet dunes, and they describe those as well. These illustrations are taken from Nigel Mountney, who modified Gary and Karen's black and white diagrams, but they really did the fundamental work, and Nigel's just built on it by incorporating a third component, which is sediment supply. With more and more sediment supply, obviously you can build more dunes, but what they do, they become drier because they become higher. You get less inter-dune, generally wetter, still sand. Sometimes there's some fluvial that can wash in there, but mostly it's just a wet Aeolian sand that's the water table is near it. So in dry dunes, they tend to climb up each other's back, and you don't get it. So in this chart right here, a relative water table, you really like to have a water table about the same rise as Aeolian accumulation rate. So you can preserve it, but you also keep the dunes high and dry. With too much drop in water level, then you can get a bypass and erosion, and too much, then you go into subaqueous, obviously with the transgression. Somewhere in here, you get some wetter dunes compared to the dry dunes. Here's an outcrop, again, from Nigel's field trip, and it shows, it's kind of hard to see, but the white here is the cross-bedded dunes, and these rosy colored ones are actually the wetter interdunes. So this is a combination, it's kind of a wet dune sequence, probably from something like here. This is just saying, dry dunes, relative water table. Relative water table can be tied to basin subsidence. Obviously, that's the easiest way, but you don't necessarily have to have a water table tied to that. In other words, water table could rise and maybe increasing rains or transgression for whatever reason, or it might fall because maybe there's a regression, not necessarily due to basin subsidence. But basin subsidence will, we do know, is going to ultimately put you down into the water table. And so you don't get as much time in the sun. So subsidence allows, so you saw this diagram before where these three wells, but locally you can find both fluvial that gets tremendously thick, this one, fluvial, tremendously thick in these potholes. And then in one particular example that I'll show at Appomattox Northwest, we got an extremely expanded Aeolian dune sequence, and permeability suffered because this expansion rate was so much that, yeah, they were dunes, but they didn't get nearly the seasoning that the other ones did out in the rain and sun. So those are just the common thicknesses of the facies shown earlier. Yeah, okay. So Appomattox Northwest. Appomattox Northwest, this is an anticline shown on the index map here. The first appraisal well was here. There's the one that we went down dip on. Then we went up here and found that one, that accumulation. Finally, the next appraisal one was to drill this well to test the continuity across this southern block, because that seemed to be the large accumulation. Got a check mark there, a nice pressure continuity of that. We're on a roll. Then we said, well, let's go ahead and sidetrack out of here and go up and drill in this northwest one. Yeah, we're mid-dip, but let's see what it looks like. And we got a big surprise. That's this one right here. Curiously, we did see the circular ring of faults around here. There is a salt dome sitting right here, which this line shows out of the plane. Forget this one. This is off here to the north. This one right here basically is a salt dome that overhangs this area. But on this line, because it's where the well is, I'm just showing it here out of the plane. But subsidence created because it was at the stock of this salt dome, and so salt went down and sediment went down and salt went up. Here is an example of a stick section showing the thicknesses across the Appomattox one. So here's that one that has the salt withdrawal and went up into it. You can see, sometimes there was salt movement during the time of deposition, and it's no surprise. I think recently they've had some other surprises, although I don't know exactly what all the other appraisal wells are, but I do know that there's thickness variation. The depositional model is one where the winds blew off to the northwest, piled it against this. Here's where the salt dome is, and there's actually an overhang that comes out about this much. And it looks like that the sediments just piled on here, dropped down, deflated, increasing the subsidence rate locally in this area. Here is an Appomattox structural history showing that as here's the initial salt withdrawing, then the Smackover transgression. This fault didn't seem to have quite as much. This is very important during this time because it's used as a proxy maybe for the uppermost Norphlet, which I'll show in a little bit, had a better permeability than the stuff down below. So the fault may have slowed kind of during the Smackover time and then picked right back up here in the Kimmeridgian time before it kind of bottomed out. And then we did some tilting to the north and then to the south to kind of rock and roll the structure up into the nice anticline that we see today. Comparing the Smackover thickness across the fault, this is the upthrown side, this is the downthrown side. So the basal conglomerate, the basal the basal carbonate had expanded only about 1.7 times compared to the upper, to the upthrown side. And you can see this is about 2 times thicker. If we look at shallower, this is up to 4 times, and this is 2 times. This is up in the Kimmeridgian. But if we really focus down on the Norphlet, what I tried to do was to measure the millions of years from the chart here, how long the basal Smackover was, how much time for the Kimmeridgian, and then plot the thickness of that true vertical thickness on the downthrown side. And we can see that these are the times here, and this is in depth, that the Norphlet, and that didn't see the base, so this thing could even be steeper, that somewhere here there's a slowdown. So this would have been fast subsidence and then slower subsidence. So maybe it could be used as a proxy for near the top of the Norphlet. Here is a cross-section schematic. This is the Appomattox Northwest, never sell the salt. But if the Smackover didn't expand very much, perhaps, it indicates that the uppermost, the last dune sequence up in here, which by the way looks like it's trying to dry upwards much more than down in through here, which are more sand sheets and dunes that didn't dry up as much. We normally see this pattern on dip meters. Look at here, 46 millidars of permeability, 38. Porosities are always okay. I mean, this is still better than 14. But the key thing was this had shows in it, meaning that it was enough to draw the charge downward into it. And so even though it's a dry hole, it did have shows. And although to my knowledge, it hasn't been done yet. This is where the position is structurally. This might have detected, often we'll see bleaching and some shows within 30 or 40 feet of the oil-water contact. So if you put one there and you draw a structure map, now you only put this much thickness because you don't know if it's going to get any better permeability or not. That's going to decrease some of the volume. You could have an attic volume remaining up dip potential here. I don't know whether they've done it or not, but who knows. So in summary, burial history, recent burial is key. Minimum Smackover source rock maturity, got to get the heat up. And finally, you need good and effective permeability found only in the Aeolian dunes section. So I think that's it. And thank you for your time. I appreciate it. Any questions?
Yes, we already have a couple questions. I'm gonna unmute Mike Sweet.
Okay.
Hi, can you hear me?
Yes.
Good. So, hey, a couple of questions. I'm Mike Sweet. I've worked on the Norphlet before. So do you see evidence with the red shale? Kind of implied it that you might actually see some of the relic dune topography preserved. As you probably know from Mobile Bay, that's always been kind of a debate about how much of those elongate thicks or relic dune topography versus subsidence into the underlying salt.
Right. That is true. I've looked at a lot of cores at Mobile Bay, and I have seen some of the red shale, some, and you know, there may be some. The whole key thing is what my question is. Mobile Bay is more up dip in the sense than maybe some of this depositionally. You know, when it happened, and one of the things that would be very interesting to note. Would be to look at some of the onshore wells. Obviously we have a lot. There, I think the transgression, you know, obviously would have started earlier, more basinward, no kidding. But as the Smackover transgression went upwards, I think two things happened. One, you're covering more of the previous salt, so maybe the salinity differences become less, and maybe you get a little bit more critter, maybe a little more higher energy. Maybe there could have been some erosion of the dunes there at Mobile Bay. So I'm not saying that there isn't. I have looked at some there, but so it'd be interesting. There's a lot of core and everything to really go back in and see, look at the red shale, look at the very top to see if you see any sloughing or erosion kind of, or you know, there's that whole tight zone. But I don't know. I don't think that's part of a transgression. There's some other ideas on the tight zone distribution because it can be quite variable. Sometimes it can be really thick, other times it can be thinner.
But in the deep water play, do you think you see evidence of actual dune topography preserved,
Oh,
or
yes.
do you think that that's what I want to get at? Yeah. Okay.
Yeah. No, I think the idea, even though it wasn't real clear, I think I'm trying to allude to it by having 30 or 40 feet where there's no topography, and yet, you know, only a few feet of this diagnostic shale over the top. So one way to get it is just entomb it. So
Right.
yeah,
And one last quick question while I'm here. The low permeability you see in the fluvial facies, what do you think's driving that? Poor sorting, lack of chloride overgrowth, or is it just the different? Okay.
It's lack of chloride over. I mean, they have them. They clearly do. But it's one of these things where it might be 50%, 60%, 70%, and it doesn't matter because it gets cemented up. You've got to have 98%, and the only way to get 98% is basically have it in the Vado zone and have rains draw down. If it's already water lane, the water table is nearby. So and also water can knock off clays and things too, which is detrimental. So that's the whole thing, really.
Okay, thank you.
Sure.
Mike Hudak, you're next, please.
Okay, yeah, I was noticed in your reconstruction of the deposition for Norphlet, you had what I guess I'd call a minimalist translation interpretation for the chip distribution.
Yes.
So how do you respond to people who want to say that the chips were at one point completely all touching each other and that all of the gaps are extensional?
Well, so first off, there, with the Cretaceous margin, and you know this, with the Cretaceous margin, it's hard to image underneath. So there could be additional chips, whether they're small or big, probably smaller. The smaller chips seem to be near the front, but regardless, it's an unknown. And so if you didn't put any chips there, then you could, you know, really ram the observed chips up against there and have a big translation. If you decided to put chips in there, but you just couldn't resolve it, then obviously you couldn't pull them all back as much. I just chose to do more of a minimalist, only because from an exploration standpoint, we've kind of seen that all of the wells that have been drilled on the chips that are exposed and, you know, where we have prospects, seem to have a fluvial domination in these more up-dip areas. And so anything more up-dip than these up-dip areas, you know, from an economic standpoint, it's kind of like, I doubt if there's Aeolian back in there. I mean, it could blow up against the mountain as well, but now you've got seep seal issues and things like that. And so I just chose to kind of do more of a minimalistic, but I don't know that, you know, that they weren't translated further. I do think that depositionally, there is a relationship during the Norphlet that they were together. It's just how far reconstructed together are they is the question.
Okay, thanks.
Yeah.
Frank, can you hold a minute? Oh, I need to let Mark Schuster to jump in because he had another meeting.
Yeah. Hey, Ted, can you hear me?
Yes, I can, Mark.
Yeah.
Hi.
Hey, excellent talk. It really brought back some great memories and also some not so great memories. For example,
Yeah.
Petersburg, you know?
Yeah,
Hey, one thing you didn't mention in the talk was pyrobitumen. And if you remember back to Vicksburg times, you know, that was a big deal.
Oh, it was
And do you have any thoughts on that now? You know, and I don't even know if it's been observed in some of the other wells.
Yeah.
Oh, yeah.
Yeah. So the pyrobitumen was well documented from Vicksburg, both in APG talks and things. The Vicksburg well, the B well, is by far to date has seen more than any other well. Now all wells see them, and the reason that they see them is because there's that clay rich and the clay poor. So those algal laminated, that carbonate one, they actually mature a little, just slightly earlier, and there's a lot of asphaltenes with it. And so in every single well, there's these asphaltenes, so some are pyrobitumen depending on the temperature, and other ones are just heavy asphaltenes. We can see that some components are movable, but some of it is actually pyro. So we have to, you know, there's been a lot of studies on that, but from a standpoint of finding it, Vicksburg, as you remember, the one that we drilled, the first one, was rather unique in the sense that it was a thrust fault with this Smackover sitting underneath it, and we drilled up near kind of the crest of it, such that it was almost like a donut in the sense that Smackover was above it and Smackover was below it. And so the first thing that comes out is this asphaltene, and where the well drilled, I think, saw the maximum exposure to it. Every other well has not really seen this you know, big under thrusting or of Smackover. So it's just what comes down from above. And so far, it really hasn't been a problem. But you're right, we struggled with that. And you know, if we'd have drilled any of the other wells first, I think we would have had a couple of years start on it. But,
Yeah, absolutely. Hey, thanks for that. Appreciate it.
Hey, Frank, thank you.
Hi, yeah, I thought that was a great talk. In one of the almost the last slides, you showed a subsidence rate chart in millions of years. Now that kind of implies you know the age and the rate of deposition of the Norphlet. So how'd you get that?
Well, so what I did was on that last one was I was really using the Smackover as a proxy for the uppermost Norphlet. You're right. There's no way in the Norphlet that we could you know, do the ages. What I did is I just said just kind of the normal chart that people have, and of course it's changing all the time with the age of the salt, you know, at 170 million years versus, you know, maybe before at 100 and whatever, 63 or something. you know, so it's changing, but we didn't see the base. So the Norphlet is an unknown. But what I tried to do was I said, okay, the Smackover itself, we do have some stratigraphy. Certainly had log characteristics that you could correlate. And we know where the top of the Oxfordian is, which is basically at the top Smackover. So you kind of, you know, I was using the Kimmeridgian basically at the top Smackover, I don't have an age date for what the basal Smackover is. So it was just really, it's not very rigorous, but I was trying to explain how could the very top part of that Appomattox Northwest have some pretty good, you know, and we looked at the cores and they have, I mean, they have chlorite coatings that are better, and obviously it's got better permeability and it got a charge. So, you know, the idea was, well, why didn't the rest of it? And we could clearly see that the bottom dropped out pretty rapidly. And so it was just a way to kind of stimulate some thought rather than a rigorous, I know the ages.
Okay.
So you're right.
Thanks.
Mm-hmm.
Tongwei, you're next.
Hi, Ted, and
Hi.
great talk. And in your slides 8 and 9, you show the downward oil charge from source rock to underneath sandstones.
Yes.
So my question is, do you have any ideas about what kind of the migration path and for the oil expelled out of the source rock and charged into the downward sandstone reservoirs? Is related to the generation to create the fractures, macro fractures, or what?
Right.
Else?
Well, I think what it is the so if we come back here, so everything in around the Smackover, or even in the Kimmeridgian, is all pretty. It's all pretty tight. It's very hard to actually get, you know, pressures, MDTs or anything, because there's nothing really detectable. But we do know that in the Smackover, in the source rock, we see, when we take sidewall cores, we see that it's just full of oil that's already come out. And the first thing it would do, of course, would fill all the microporosity or any sort of any kind of little fracture, or any kind of porosity that would be there. And then, but if it can't escape, you know, and it's not enough to build up a pressure yet, more and more as the heat gets turned up, more and more pressure gets built, pore pressure in the sense there, and then we believe it's microfracturing that would occur both upwards and downwards. But if it goes upwards and it's still no permeability upwards, then it's got a harder time to try to force its way to the surface through less permeable rock versus hydropotential, you know, hydrodynamics in a sense. It sees the Norphlet as permeability, and it can backfill some of those stringers that probably extend upwards, you know, vertical from the source rock, and kind of fill back down and can alleviate the pressure buildup in there by going downward and then laterally up dip. You know, in other words, it can climb to a structure and at least get higher there, and then fight another day and try to migrate up from there. But I think that's what's causing it.
Thank you, Ted.
Mm-hmm.
Jill and Frank, go ahead again.
That was a fantastic talk. Thank you, Ted. I have not worked the Norphlet, and certainly not in this detail. It was just wonderful to have this this story told properly. But I did hear, and this was quite a while ago, there were rumors when one of your partners was talking at a meeting, there were rumors that one of your wells actually encountered a possibility of an additional lacustrine sourced oil. Was that ever verified?
Not while I was there. There were times when we drilled Petersburg and Fredericksburg. We went down, we drilled through the, basically there was a little bit of salt at the bottom, and Fredericksburg in particular. And so there was this kind of weird lithologies, and the geochems, they all of the sample was pretty well burned up. We did get thin sections and some small scale to kind of date. There was some basalt down in there. It looked like it was Eagle Mills. But, and then in some of the other Apo Southwest, the upthrown block, it had a pretty big expanded, I call it a dirt section underneath there. There were some shales. And they thought that maybe there was some lacustrine source in there, but that was never, there was never any to be seen in there. So to my knowledge, and I retired in 2014, I've been in contact with them, but of course they don't tell me much, and rightly so. But I've not heard anything.
Thank you so much.
Sure.
Lucy, you'll be the last one.
Okay, hi, I'm Lucy Ko. Thank you for the great talk. I learned a lot. Can you explain a little bit more on what you just mentioned earlier on the asphaltene and pyrobitumen when you answer Schuster? Were both of them like blocking throat and prevent flowing of the oil to the wellbore, or what was the issue?
So the issue was mainly unknown, but what we could tell, because we would get samples out of it, we took the whole core. We tried, and I can't think of the name of it, dichloroxide, some kind of big word, but basically pretty nasty acids and stuff, right, to try to dissolve it, and it didn't, and it was immovable. There was no way we could clean or remove any of this, and it was occluding a lot of pores, and especially pore throats. So the worry was, and we didn't test the well in terms of flow tested or anything, but the worry was, and it wasn't completely all the way through. I mean, there were places we knew that it would flow, but at what rate? And in deep water, that was a key thing. So one of the things that Mark was involved with, and when we were there, were we said, well, what do we do with this thing? We have this Nikika, which is a Miocene production facility not too far away. And we tried to say, well, could we hook this one well up and just flow test it before we build a platform or anything like that and just see if it would work? But of course, there's different pressure, temperature, and modifications, and with BP operating, and it just didn't work out. So we kind of went into a persistence mode of keep trying some other ones, thankfully. And, after that, we never saw it to the degree. But to answer your question, well, okay, let me say, what we started to learn after that by drilling different prospects that had slightly different thermal histories, some more mature than other ones, we could see that this early asphaltene product that Mark had called pyrobitumen, and rightly so, in some cases, if you looked at the Abrams, back his solid hydrocarbon thing, is it just asphaltenes, bitumen, but it's just, we could see that there was some solubility in some, if it wasn't as mature. Mobile Bay, for example, is all pyrobitumen. That's really hot, it's cracked, it's immovable, but it's also gas now. So that can flow better. But we've learned that the pyrobitumen is there, or excuse me, here I go again. The asphaltene contents are there. Some is pyrobitumen, some is not, but it's never been to the amount that was in the Vicksburg B well, the very first one that we drilled. So, and I haven't seen what the flow tests are at Appomattox that are flowing, but I don't think that the asphaltenes are a problem there. I don't know that for sure, but
thank you. So you mentioned earlier again, these are from earlier conversion of more like algal stuff, like more.
Yes. So there's two source rocks. Yes. So in this figure here that just happens to be up, there are two source rocks. One little bluer at the bottom. That's out of that basal carbonate. And what we see in there in that very first picture that had all those laminations, they seem to be algal laminations. Okay. And there's I've got a talk that could talk about how they were formed. But basically, they were algal mats that washed out hypopycnal flow out onto this very saline water. They bloomed an algal bloom, and then they sank to the bottom. That's why, another evidence for very quiet water transgression. And it was an oxenic environment, and so they were preserved. But the thing is that because they're all laminations, the kinetics of that rock is such that, well, one, they mature earlier, and it's a big line of kerogen, so they all pop each other and they expel out earlier. And it's more of an asphaltene rich, whereas the clay rich, more of a marl that's actually richer, thankfully, which is that lighter blue-gray one up above on this little diagram here. It comes in and it's a much better quality oil without the asphaltenes. And so you get a mixing of that in there, and so you get a much better oil when you get that contribution in there as well.
Thank you for answering this. It's really interesting. Thank you.
Ted, this is Scott Tinker talking, and thank you for a great talk.
Hi, Scott. Thank you.
We appreciate it very much, and for you adapting to these kinds of presentation, but it's not bad.
Like the dress code.
You've had a nice audience all morning on the phone here, so thanks for doing that, and everybody else at the Bureau, we look forward to hearing from you at 1 o'clock today. We've got all staff actually on Zoom at 1 o'clock, and Ted, good luck with it. We appreciate you joining us.
Okay, well, we'll see. Yeah, thanks.
So great talk. Thank you, Ted. How about give him a virtual claps? Yeah, actually we can't do that. I think on the on the participant side, so they may show up. Yeah. Well, thank you very much.
All right. Thank you very much. I appreciate it.
Okay. So see everybody either this afternoon or next Friday. Bye. Thank you, Ted.
Thank you.
I'm gonna end the meeting.
All right.